The idea was that if I take my bipolar transistor and I short its base and collector and I pass a current. So what we are doing is by shorting base and collector, we are converting the transistor into a diode. Right? It's a diode. And I pass a current through my transistor here. Now in this case, it's easy to show that the current I0 is basically the emitter current. And because the transistor is in active mode, emitter current is almost equal to collector current. We have a beta of around 200 or more. So emitter current is almost equal to collector current. And from theory, we know that it's Is exponent Vb by Vt. Vt is the thermal voltage. Okay. So this is the relationship. So the idea is that suppose I pass a certain current, I0, and I measure this value Vb. Then I can invert this equation and I can write Vb is Kt by Q, ln I0 by Is. I know the value of I0. I'm forcing a particular I0 into my circuit, so I know I0. And I'm measuring Vb. And I want to know temperature. So there is a problem. There is this Is term also there. Right? Is term is also there. And Is term, the saturation current, is also a function of temperature. So that creates a problem. I want to measure the temperature by simply measuring the voltage here. So very simply what I can do is the following. I can pass I0, measure VB1, and then I can pass a current which is N times I0, and then measure VB2. VB2 will be Kt by Q ln N times I0 by Is. So I measure VB1 and I measure VB2 and I take the difference between the two. If I take the difference, VB2 minus VB1 is equal to Kt by Q ln times N. Right? So now it's straightforward. All that I need to do is pass a current here, pass a current which is N times here, measure VB1, measure VB2, take the difference. Easy to take the difference. I know the ratio here. And therefore, from this ratio, I can calculate what is the temperature. But the temperature that you get here is in degrees or Kelvin? Kelvin. So if I want my actual temperature in degree, then what I need to do is VB2 minus VB1 divided by ln N multiplied by, why am I doing this? Will this give me the temperature in Kelvin? Look at this multiplying factor. All of you know what is the thermal voltage for room temperature? 0.0. Normally we take 0.026, but more precisely 0.02588. And so this will give me the temperature in Kelvin. And I subtract 273. I will get the temperature in degrees Celsius. So that was the idea behind measuring the temperature in the lab. Taking your bipolar transistor, passing a current I0, then passing maybe one could choose a current of 1 microamperes, choose a current of 100 microamperes or a milliamperes, measure VB1, measure VB2, subtract and calculate what the value of the temperature is there. Okay? Looks fine? Alright, let's give an example. Say 1 microamperes. If you had passed 1 microamperes into your transistor in the lab, you would have probably measured 0.468 volt here. If you had passed, let's say 1 milliamperes, you would have probably measured 0.654. These things vary from diode to diode also, 0.654. Then, what did we say? We'll take the difference of the two, VB2 minus VB1. What is N for us? 1000. And therefore, I can calculate the difference VB2 minus VB1, which is 0.187. And Kt by Q, ln of 1000 is 6.908. And from there, I get a T of 313 K. And then temperature in degrees Celsius, all that I do is take all this term, subtract 273, and I get a temperature of 40 degrees Celsius. So this is what I was expecting, that you would take a bipolar transistor, pass two different currents, measure the voltage VB1 and VB2, and from there find out what is the temperature. This, of course, is the temperature of your transistor, right? Now, things look fine, right? It looks like a very nice technique for measuring temperature. Everything, you have any doubts that it will work? It will not work? I've explained the entire theory to you. Transistor, very simple. Pass a current of 1 microamperes is not difficult. 1 milliamperes is also not difficult. Take the difference, calculate the temperature. Straight. There's no problem with the theory. Theory is absolutely fine. If you're worrying about is this equation really true, it is true. Okay, lots of measurements, lots of these things have shown that IC does go as exponent of VB by VT. There's no issue with that. So there's no problem with the theory that you see here. In theory, things should work fine. In practice, will it work fine? That's the point that I'm trying to raise. In theory, everything is fine. It's like a very simple, very nice technique, and I should be easily able to measure 40 degree, 45 degree, whatever is the temperature, I should be able to measure. In practice, will there be a problem? I mean, forcing a current of 1 microamperes into a diode is not an issue. Forcing a current of 1 milliamperes into your transistor is not an issue. No problem. Easily you can force these currents. And they're all reasonable currents. 1 microamperes and 1 milliamperes, they're all reasonable values. I'm not asking you to force a picoamperes where you'll say, oh, where will I get a picoampere? Microamperes are very easy to generate. 1 volt and 1 mega ohm will generate 1 microamperes. Where is the problem? Huh? What? Okay, so he's raising a point that what I'm measuring is the temperature of the transistor. What he's raising, the issue is that when 1 microampere current flows through it, what is the power dissipated in the transistor? Roughly, power dissipated in this case would be how much? 1 microamperes multiplied by 0.468. That's the power dissipated here. And here is 1 milliampere multiplied by 0.654. So you have a valid point, but you know, for BC 547, if I look at the power calculation, I'll find that the power dissipated in both cases is sufficiently small so that the temperature is going to be very close to the ambient temperature. These power dissipations are not high. If I were to force very high current, then you're right, the temperature of this transistor may be different from the temperature of this transistor. That's a very valid point. But I can arrange the currents such that the power dissipation in my transistors are very low. So both the transistors are at reasonable temperature. That's a very valid point that this one transistor could be at a different temperature than this. But I can arrange the currents such that the power dissipations are not high and the currents are almost the same. The temperatures are almost the same. Mm-hmm. So the temperature would at least be 70 degrees or so. All right, that very valid point. Let me introduce. So remember now, the moment you go to the lab, you're absolutely right. The moment you go to the lab, when you measure 0.468, you think you're going to measure 0.468? Have you seen? Let's say you put a signal in the oscilloscope. What do you see? I mean, you press measure and what do you find? Is it always 0.468 or will it be 0.469, 0.46? It keeps on fluctuating. There is an error. The moment you measure something, there is always an error. And so, when you have a nice theoretical technique which works fine, you should see then how sensitive is my technique to errors. So suppose now I introduce an error of 1% in the measurement of voltage. It's a small error, 1%. Now the error, as you can understand, could make this voltage 1% higher or 1% lower. Similarly, the error here could make it 1% higher or 1% lower. So let me make this 1% lower. A value equal to. So impact of 1% error in measurement. I make this 1% lower. So it becomes 0.463. And this one I make 1% higher. And it becomes 0.661. Now, what would happen to the difference? Difference will change. And the change in the difference will result in a change in temperature. How much is the change? The new, because of this 1% error, the new temperature comes out to be 331.8. How much is the error? 6%. 1% error in this one and 1% error in this one translates into 6% error here. Why? Because whenever you take difference of the two quantities, you are in trouble. Two quantities which are close to each other, you are in trouble. The errors get amplified. But that's not all. What is the error in? I'm also, if you note that, I'm interested in temperature in degrees Celsius. So now if I take this value of VB2, VB1 and all that and calculate, what do I get? 58.8 degrees Celsius. And my error is 47%. So 1% error here, 1% error here translates into 6% error here in temperature measured in Kelvin, and temperature measured in degrees Celsius translates into 47% error here. So it may be 40 degrees in the lab, but then you may create a world record by saying it's 58.8% at degrees Celsius. All right. So very nice theoretical technique. You find it should work fine, but then you find that it's quite sensitive to errors here. So if you want this particular technique to work, what you'll have to do is measure these voltages very, very precisely. If you can measure voltages in a millivolt, very, very precise measurement here, then you can measure your temperature properly. Otherwise, there's going to be significant errors. 1% error is translating into 47% error in this particular temperature here.